Hello everyone. This is the third class on the mechanics of solids. In this class, we will study the non-uniform bending. What is non-uniform bending? In non-uniform bending, the beam is supported its end and the beam is loaded at the middle. Now the beam undergoes bending and that bending is non-uniform. Therefore it is called non-uniform bending. The non-uniform bending is shown in the picture. This is the beam. The beam is supported at two ends by a knife edge. This is one knife edge, this is another knife edge. That is, the beam is supported at two ends and the beam is loaded in the middle as shown in the picture by a weight W. Now the beam undergoes bending like this. The beam undergoes bending like this. Now this bending is non-uniform. So in non-uniform bending, the beam is supported its end and loaded in the middle and the beam bends and the bending is non-uniform. So what is our aim? Our aim is to find out the depression at the middle point. When you load the beam in the middle portion deflects. How much it is deflected? That gives the depression at the middle point. So in this section, our aim is to find out the depression at the middle point. Let the length of the beam be L. Now in the picture, AB represents a rigid uniform beam which is resting symmetrically on two knife edges K1 and K2. Now A and B of the rod is separated by a length L. So we will say the length of the beam is L. The distance between A and B is L. Now the beam is loaded at the middle point of the beam. It is represented by capital D with a load W is equal to mg. So the beam undergoes bending as shown in the figure. Now the reactions at each knife edge is W by 2, that is acting vertically upwards. That is, the reaction at one knife edge is W by 2 and another knife edge is W by 2. It acts vertically upwards. And we can say that the beam bends symmetrically with respect to D. D is the middle point of the beam. And the depression is maximum at the point D. Now our aim is to find out the expression for the depression at the middle point. How much the middle point is deflected when it is loaded at the middle point. So our aim is to find out the expression for this depression at the middle point. The schematic diagram is shown in the right hand side. It represents the non-uniform bending as I specified. AB is a rigid uniform beam resting symmetrically on two knife edges K1 and K2. Now A and B are separated by a distance L. And L is called the length of the beam. Now it is loaded at the middle point D with a load W is equal to mg. Now the reaction at each knife edge is W by 2 and that is pointing upwards. Now the beam bends symmetrically. The beam bends symmetrically with respect to the middle point D and the depression is maximum at the middle point D. So our aim is to find out how much the middle point is deflected by the action of this weight W. So we have to find out an expression for the depression at the middle point. Now we can see that because of the symmetry of the bending, the tangent at D is horizontal. I have drawn a tangent at the point D, which is represented as a red line. I have drawn a tangent at D. You can see that the tangent at D is horizontal. Horizontal. That is, when you look the beam from the bottom side, you can see that there is no elevation at the point D. At point D, there is no elevation, or we can say the beam looks like it is fixed at the point D and it is elevated at each ends. The beam looks like it is fixed at the point D and it is elevated at two ends. So we can conclude that each half of the beam, that is whether it is DA or DB, we can consider it as two cantilever of length L by 2 fixed at D and loaded with weight W by 2 at the ends. So what is our conclusion? The tangent at D is horizontal means we can consider this kind of bending as two cantilever of length L by 2, that is fixed at D and loaded upwards with a reaction W by 2 at the ends. So actually this non-uniform bending can be considered as a combination of two inverted cantilevers, that is the cantilever that is bent upwards and fixed at D. So we can say that the beam bent, that is this non-uniform bending, is equivalent to two single inverted cantilevers fixed at D, each cantilever having length L by 2 and it is loaded at the knife edge with weight W by 2. So we can consider this situation, which is a combination of two inverted cantilevers, that is a cantilever which is bent upwards. The cantilevers are fixed at D and it bends upwards with weight W by 2, which is pointing upwards. Here W by 2 is actually the reaction force. W by 2 is the reaction. Here W by 2 is acting vertically upwards. Now one such cantilever is shown in the figure below. One such cantilever, that is the cantilever on the right hand side, is shown in the figure. We can consider non-uniform bending is equivalent to two single inverted cantilevers fixed at D, each of length L by 2 and loaded at K1 and K2 with weight W by 2. And consider the cantilever on the right hand side, that is inverted cantilever on the right hand side, which is fixed at D and loaded at the end B. Now consider, if you consider a point C on the inverted cantilever, then the elevation at C is Y, where C is at a distance X from the fixed end D. That is, in the figure, an inverted cantilever on the right hand side is shown. B is the point where it is deflected upward with the elevation delta. So we can see that at B the reaction is W by 2, or at B is deflected upwards with weight W by 2. Now it is fixed at D. Now what is our aim? In this section, our aim is to find out the depression at the middle point. in non-uniform bending, our aim is to find out the depression at the middle point, because at the middle point the beam is loaded and we have to find out how much the middle point is deflected. That gives the depression at the middle point. Now we have seen that this bending, when this type of bending happens, it is equivalent to two inverted cantilevers having length L by 2 and which is loaded by a weight W by 2 at A and B. One such cantilever is shown below. Now we can clearly see that because of the symmetry of the bending, we can see that the depression at the middle point is equivalent to the elevation at the loaded end. We are using this assumption to derive the expression for the depression at the middle points. So what is our assumption? That is the elevation of the loaded end. The elevation of the loaded end means the elevation of the loaded end of the inverted cantilever is equal to the depression at the middle point when the beam bends non-uniformly. That is, the elevation of the loaded end is the same as the depression at the middle point. Elevation of the loaded end is given by delta. Delta is the elevation of the loaded end, which is at a distance L by 2 from the middle point D. Here two cantilevers having length L by 2 are taken. Since the total length of the beam is L and the beam contains two cantilever, we can see that the total length of the cantilever is L by 2. Now you consider a section C inside the beam which is at a distance X from the fixed end where the deflection is Y. Delta is the maximum elevation that is produced at the loaded end of the inverted cantilever. So what is our aim? Our aim is to find out the depression at the middle point when the beam undergoes non-uniform bending. So we have assumed that the beam, when it bends, it is equivalent to two inverted cantilevers which is fixed at the middle point and loaded at the opposite end. Why the beam bends? Because of the weight W which is acting at the middle point. Now the depression at the middle point is same as the elevation at the loaded end. Loaded end means the end of the inverted cantilever where the reaction is acting. Here the inverted cantilever bend upwards due to the reaction W by 2. So the loaded end means it is at the knife edge. Now in the figure, the loaded end is B where the reaction is W by 2. So the elevation of the loaded end means the elevation at B that is equal to delta. That is elevation at the loaded end which is equal to delta. Now once you find out this elevation at the loaded end, that is equal to the depression at the middle point. Here also you have to consider the fact that the external bending moment is equal to internal bending moment. What is internal bending moment? That is equal to Yig divided by R that we have already discussed. To derive the expression, let us consider a portion C on the beam. To derive the expression, consider a section of the beam at point C. Let us consider a section of the beam at point C. Now C is at a distance X from the point D, where D is the middle point. Now this is the section we have to consider. C is at a distance x from the middle point, and the total length of this inverted cantilever is L by 2, and you have to consider this portion, and if the distance between D and B is L by 2, we can clearly say that the distance between C and B is L by 2 minus x. Now let us find out the external bending moment, that is the bending moment corresponding to the external couple. The external couple is bending the beam, so the bending moment corresponding to the external couple, that is called the external bending moment. Now the moment is always equal to force into perpendicular distance. Here the force is W by 2 and the perpendicular distance is the distance from the point under consideration. Here we are considering the point C. So with respect to that point C, the perpendicular distance is L by 2 minus x. Therefore the external bending moment is W by 2 into the distance L by 2 minus x. We have already seen the internal bending moment, that is due to the restoring couple, that is equal to yig divided by r. Now at equilibrium, this external bending moment is equal to the internal bending moment. That is at equilibrium, this external bending moment is equal to the internal bending moment. Because at equilibrium the beam is balanced, the external bending moment balances the internal bending moment. So you can say W by 2 into L by 2 minus x, that is equal to yig divided by r. W by 2 into L by 2 minus x is equal to yig divided by r, from which 1 by r is equal to W divided by 1 by r is equal to W divided by 2 yig into L by 2 minus x into L by 2 minus x. Now what is 1 by r? Now 1 by r is approximately equal to d square y by dx square, where r is the radius of curvature. Now substitute for 1 by r as d square y by dx square, that is equal to W divided by 2 yig into L by 2 minus x. That is, we have d square y by dx square is W divided by 2 yig into L by 2 minus x. Now integrate this equation. Now integrating this equation. Now integral of d square y by dx square is nothing but dy by dx. Now dy by dx is equal to W divided by 2yig into integral L by 2 minus x dx. That is W divided by 2yig into, now L by 2 is a constant, therefore the integration become L by 2 x, that is Lx by 2 minus x square by 2 plus a constant of integration c1. Now we have to evaluate this constant of integration. So how do you evaluate the constant of integration? We have at x is equal to 0, dy by dx is equal to 0. X is equal to 0 means x starts from the middle point. At the middle point we have seen that there is no elevation. So at x is equal to 0 we have y is equal to 0, also dy by dx is 0. That is, at x is equal to 0, dy by dx is equal to 0. Hence, just to substitute dy by dx is equal to 0 there on the LHS and x is equal to 0 on the RHS. Now 0 is equal to W divided by 2yig into L into 0 by 2 minus 0 square divided by 2 plus C1. This implies that C1 is equal to 0. C1 is equal to 0. When C1 is equal to 0, dy by dx becomes dy by dx is equal to w divided by 2yig into w divided by 2yig into lx by 2 minus x square by 2. Lx by 2 minus x square by 2. That is, we have dy by dx is equal to w divided by 2yig into lx minus x square by 2. Now again integrate this equation. We will get y is equal to integral of dy by dx is y. So y is equal to w divided by 2yig into integral lx by 2 minus x square by 2 dx. This implies y is equal to w divided by 2yig into integral lx by 2, that is equal to L by 2 x square by 2 minus integral x square by 2 is 1 by 2 x cube by 3 plus a constant of integration C2. Here again we have to evaluate the constant C2. So what is our y? Y is equal to w divided by 2yig lx square by 4 minus x cube divided by 6 plus C2. Now what is the value of C2? We have at x is equal to 0, there is no elevation of the beam, because at x is equal to 0 there is no elevation. Y is equal to 0. That is, at x is equal to 0, y is equal to 0. Now substitute for y is equal to 0 and x is equal to 0 in the equation. We will get the value for C2. At x is equal to 0, y is equal to 0. This implies we can say 0 is equal to, just to substitute y is equal to 0 in the LHS and x is equal to 0 in the RHS. You will get 0 is equal to w divided by 2yig into L into 0 square by 4 L into 0 square by 4 minus 0 cube divided by 6 plus C2 and this implies that C2 is equal to 0. When C2 is equal to 0, the expression for y becomes y is equal to w divided by 2yig into lx square by 4 w divided by 2yig into lx square by 4 minus x cube divided by 6. This is the elevation of the inverted cantilever at x from the middle point, or at x from the fixed point D. That is, y is equal to w divided by 2yig into lx square by 4 minus x cube by 6. Now what is y? Y is the elevation at x. We have to find out the elevation at the loaded end of the inverted cantilever. Loaded end means the point where the reaction W by 2 is acting. At the loaded end of the cantilever, x is equal to L by 2 because the length of the cantilever is L by 2. At that end, the elevation is delta. That is, y is equal to delta. The elevation is delta when the length of the cantilever is L by 2. So we can say that delta is equal to w divided by 2yig into L into substitute x is equal to L by 2. That is L by 4 into L square by 4, L by 2 whole square minus 1 by 6 into L by 2 whole cube, that is L cube divided by 8. Just substitute x is equal to L by 2 in the above equation and replace y by delta. That is, delta is equal to W divided by 2y Ig into L cube divided by 16, L cube divided by 16 minus L cube divided by 48. 48. This implies delta is equal to W divided by 2y Ig into 2L cube divided by 48. 2L cube divided by 2L cube divided by 48. That is the elevation of the cantilever at x is equal to L by 2, that is delta is equal to WL cube divided by 48 YG. This is the expression for the elevation of the loaded end B of the cantilever. Elevation of the loaded end B of the cantilever. It is WL cube divided by 48 YIG. What is our aim? Our aim is to find out the depression at the middle point when the beam undergoes non-uniform bending. And we have made an assumption that this non-uniform bending is equivalent to the bending corresponding to two inverted cantilevers, and the depression at the middle point is the same as the elevation at the loaded end of the cantilever. That is, the depression at the middle point D is the same as the elevation at the loaded end B of the cantilever. Hence, we can say that the depression at the middle point D due to the weight W is equivalent to the elevation at the loaded end B. Therefore, we can say that the depression at the middle point D is delta is equal to WL cube divided by 48 YIG, which is the same as the elevation at the loaded end B of the cantilever. So finally, we have the expression for the depression at the middle point D when the beam undergoes non-uniform bending is WL cube divided by 48 YIG. Now consider two cases, for a rectangular bar and for a circular rod. For a rectangular bar, we know that the geometric moment of inertia Ig is equal to BD cube by 12. Here, the breadth of the bar is B and the depth of the bar is D. Now the depression at the middle point D is WL cube divided by 48 YIG. The depression at the middle point is WL cube divided by 48 YIG. That is equal to WL cube divided by 48 Y. What is the geometric moment of inertia? That is equal to BD cube divided by 12. BD cube divided by 12. Therefore, the depression at the middle point is delta is equal to WL cube divided by 4y BD cube. This is the expression for the depression at the middle point when a rectangular bar is loaded at the middle and fixed at both ends. Now consider the case for a circular rod of radius r. Now the geometric moment of inertia is pi r raised to 4 by 4 that we have already seen. Now what is delta? The depression at the middle point is WL cube divided by 48 YIG, that is equal to WL cube divided by 48 Y. Now Ig is pi r raised to 4 by 4, that is when a circular rod undergoes non-uniform bending, the depression at the middle point delta is equal to WL cube divided by 12y pi r raised to 4. WL cube divided by 12y pi r raised to 4.